In math, we have some very important constants, values that are very specific and developed from some particular relationship. You've probably already encountered pi in one way or another. Now what we want to do is introduce the mathematical constant e. It comes from this very particular expression, 1 plus 1 over n, that quantity raised to the n power. What we want to do is plug in some different values for n and see what result we get. You could do this manually on your own with just a calculator or with an online tool. But if we plug in 1, we would get 1 plus 1 over 1 to the first power, which would just give us 2. If we plug in 2, we would get a result of 2.25. Then if we start plugging in larger values, like 10, we get 2.59374 and a decimal answer that keeps going. If we plug in 100, we would get 2.70481 and a decimal that would just keep going. When we plug in 1,000, we would get 2.71692, and those decimal values would keep going. At 10,000, we would get 2.71826. And we can start to see a little bit of a pattern emerging that we're getting values that are about 2.7 something, something, something. And then as we jump to an even larger value, 1 million, then we would get 2.71828, and again, those decimal values would continue going. So our constant e is defined by taking this expression, 1 plus 1 over n to the nth power, as our value for n goes to infinity. As we continue plugging in larger and larger values, we would get closer and closer to this approximation for e, which is 2.718281827. And really that decimal value would just keep going infinitely on. But this constant e is something that we use particularly a lot with exponential functions and mathematical modeling. And what we end up with seeing a lot is the function e to the x, which is referred to as the natural exponential function. For our purposes, what's really important to keep in mind is that when we see an expression like e to the x, what we have is a constant being raised to a variable power. So we still have an exponential function. We just need to recognize that e doesn't represent a variable. It represents a very specific value, which is about 2.7. But all the other ideas that we've talked about with exponential functions still hold true even when we're using this new value. So in example 5, we want to determine whether the functions below could model exponential growth or decay and identify the growth rate. When we talk about growth rate, what we're interested in is the coefficient in front of the variable in our exponent. So n of x equals 4e to the 5x could model exponential growth because our growth rate of 5 is greater than 0. And v of x equals 10e to the negative 9x could model exponential decay because our growth rate of negative 9 is less than 0. In example 3, we're given two functions, and we again want to identify the function with the faster growth rate and identify the function with the larger initial value. For growth rate, again, we're going to compare the coefficients of the variable in the exponent. In this case, h of x has the faster growth rate because 7 is larger than 3. And then in part B, we want to identify the function with the larger initial value. This is where we look for the coefficient in front of that exponential function or exponential expression. And in this case, we would say that h of x also has the larger initial value because 9 is larger than 2. So when we compare these two functions, h and k, h has the larger initial value. So again, if we were modeling a population, that would be the situation where we have a larger starting population, and that population is going to grow at a faster rate.